All right, guys. We're going to try to work through the rest of section. I believe it's 3-4, and there's a couple rules and theorems that I want to address that are going to help you kind of expedite your process in regards to factoring these things. Okay, because it does get cumbersome. Okay, it does get kind of problematic because when I look at those things up there, when I look at those P over Qs, and we did this one yesterday, but we started at 1, tried it, didn't work. Tried -1, didn't work. Went to 1/2, it worked. Okay, but you're going to find that some of these, as you progress through them, you might not get till like 6 and -6 or 3 and -3, halfway or even more than halfway through all your P over Qs before you start seeing ones that work. Does that make sense? So you might be thinking, now it's not a waste of time, but you're thinking, okay, I'm going through a lot of these and I'm not getting anywhere. I'm not getting any solutions yet. And that's frustrating, but it does happen. So what happens, or what we've discovered, not when I say we, I'm talking about like famous mathematicians, okay, have dealt with this for their entire lives, have determined there are some relationships that exist that allows us, as we're moving through the synthetic division. If the synthetic division gives me results, awesome. But if not, I can still look at my quotient, and my quotient might still tell me something I can do. Okay, it might allow me to eliminate some of my P over Q options. And I'm trying to give you two theorems today that kind of address that. Before we get into those, though, I want to make sure that we did finish this one yesterday. But the bell was ringing, so I want to go back through it and just remind us of some technical things that we always have to pay attention to when we're doing synthetic division and when we're doing this essentially factoring. Okay, we tried. I think it was 1/2. Brought down our 2, multiplied, gave me a 1. Brought down the 2 again, multiplied, gave me 12. Nope, that's stupid. Give me 1. And that gives me -12. Add those together, or sorry, multiply those together, give me -6. Add those together, gives me 0, right? Okay, so that's the synthetic division process. If that gives me a 0, it tells me that x minus this, okay, is a factor, right? Okay, so x minus 1/2 is a factor. All right. The next thing I do, guys, and this is kind of what we talked about yesterday, if I gave you a number like 45 and asked you is, one or two factors of that, and let's not do 45 because there's only 2, let's go 36. If I gave you 36 and I asked you are 3 and 4 factors, can I divide by 3 and get 12? And then if 4 is a factor, shouldn't 4 go into 12? Does that make sense? Okay. Where if I would have asked like the 36, let's say 36 are factors 3 and let's say 7. Okay. Well, 3 goes in there 12 times, but does 7 go into 12? No. So 7 and 3 are not factors. 3 is, but 7 is not. Does that make sense? That idea is the concept that I don't need, if I want to check any of these other things to be factors, I don't need to go back up to this blue line and use synthetic of that blue line. I can use the division of this. Does that make sense? I can look at this quadratic factor instead of this quotient. So here's the thing, and this is what we always want to think about. Okay, now, obviously yesterday we approached this a little bit differently because this was x cubed, right? And if I divide it by a factor, a linear factor, it turns into what? X squared, okay? And I want you to pay attention. Whenever you get x squared in your quotient line as your highest degree, come to the side and attack that thing with your quadratic factoring techniques. Do not continue with synthetic division because synthetic division might waste you time. Does that make sense? Okay? Our whole goal here is to be efficient. And synthetic division is not all that efficient in comparison to our quadratic process. Okay. Now, that being said, let's kind of look at this. Let's say this was like x to the 4th, this became x to the 3rd or something like that. We don't know, just because x minus 1/2 was a factor once. We don't know whether it's got multiplicity of 2. It could be a double root. It could be a triple root. Does that make sense? So when you do see if you get a 0 from one of these factors, you have to check it again. Does that make sense? Okay. Now if I were to check that again here, bring my 2 down, gives me 1, bring my 3, gives me 3/2. Obviously, that is a non-zero number right there, right? So that proves then that it does not have a multiplicity of 2, it only has a multiplicity of 1. Does that make sense, everybody? Okay. So now the question is, what do I do from here? Okay. If this is 2x squared plus 2x minus 12, what can come out of both, or all of those? 2. So it leaves me with x squared plus x minus 6, right? Now what's that factor to? Okay. Positive 3, negative 2. And I've got that 2 up front, though, right? What does that tell me? That means that if I would have came over here and I would have used, let's say, 2. Take my 2 down, gives me 2. Multiply gives me 4. Add gives me 6. Multiply those together gives me 12, right? Is that a 0? Okay. But it might have been a while before I tried 2 again, right? Okay. Now in this one, it would have been maybe I would have tried negative 1/2, and then I would have jumped right to 2. So it wouldn't have been too long, but the process of factoring this way is a little bit quicker. Now, if that's x squared and this is x to the first, okay, well, doesn't that mean 2x plus 6? Well, how does that factor? Gives me that right there, doesn't it? Okay, so there's alternate techniques, and they should validate one another, right? My thought is, guys, whenever we get down to x squared, though, if you want to keep going with it, by all means do it, but you're going to waste your time, okay? Once you get x squared in the quotient row, go straight over to your factoring technique, okay? And one of those techniques, guys, might be the quadratic formula, okay? Because that will happen quite a bit, and there will be times where we get, and we'll talk about this maybe tomorrow or the next day, we might get a quadratic. Let's say that we get a quadratic, but right now we're at this here, okay? We could have a quadratic in which none of these are possible, or none of those become factors or zeros. Does that make sense? Because we know some quadratics do not cross the x-axis, right? Okay? So we could end up with this producing non-real solutions. Well, these are only possible real solutions, right? So we could get to this point right here real early on, and then go through and divide by all of these things throughout, and find out that none of them work. And then you're going to be frustrated and say, well, I did all that work, nothing came out, now what do I do? Well, now you turn to your quadratic formula. Well, would it have been nice to turn your quadratic formula right away and not waste all that time? Okay? So that's kind of the mindset that we want to take as we go through these. Okay? Now, I want to do another example of this, but before we get through like the entire example, we'll kind of stagger this a little bit, and we're going to introduce some concepts as we work through, and then try to use those concepts. Now, I'm going to do this kind of in a foolish way, because right now when I look at that, I could take a 4 out of everything, right? And then I'll have x to the 4th minus 4x cubed plus 2x squared plus 4x minus 3. And in my list of p over q is going to be very simple, very small, okay? I think that's the best thing for you to do, but I'm going to neglect that right now because I want to show you, if I would have changed one of those values, changed the, the negative 16 to like a 15 or something like that. Now not everything's divisible by 4, and I would have to use this approach that I'm going to talk about. Does that make sense? All right. So does it happen? Do we get at times a 4th degree, 5th degree, 6th degree where there's a GCF in regards to the coefficient? Absolutely. Take that out. It'll make your life a little bit easier. Okay? But if you forget, you should still be able to do the work. All right, so we write down our p-values. Remember, your p-values are the factors of your constant. So it's going to be plus or minus. And I'm going to do that. I'm just going to kind of, I don't want to write plus or minus every single time. So plus or minus, and I'll put parentheses 1, 2, 3, 4, 6, and 12. Those are all my factors for p, right? Okay. Now, q That's plus or minus all the factors of my leading coefficient. So 1, 2, and 4, right? So then all my P over Q's, okay? Again, it's only going to be plus or minus, so I'm going to use that same notation. But now I go through and I look at every P value, and I write it over the top of every Q value. Now, we talked about this yesterday. If there are, there's six options for P, there's 3 options for Q, so that makes 18 total combinations that I could use, okay? But if they're positive and negative, it turns into 36 possibilities, right? So throughout this thing, we'll have 36 possible zeros that I have to go through the synthetic division with. And it might not be until the last 4 that I get my zero. So I can go through 32 iterations of synthetic division and not get a solution yet, okay? Or not get a zero. You see how that would be very frustrating, okay? So some of the stuff we talk about is going to kind of maybe help address that. I'm going to write my plus or minus, and then we're going to go through and say, okay, I'll put that one over all 3 of these. So it'd be 1 over 1, be 1 over 2, 1 over 4. Then I'm going to do the same thing with that 2. So now I'll go 2 over 1, 2 over 2, 2 over 4, and I just keep going along the line here. 3 over 1, 3 over 2, 3 over 4, 4 over 4, 4 over 1, 4 over 2, 4 over 4, 6 over 1, 6 over 2, 6 over 4, and then 12 over 1, 12 over 2, 12 over 4. And that gives us our list. Okay, now, when it gives us our list, our next thing we're going to want to do is go through and reduce those and also kind of kick out redundancies. Okay. So in regards to reducing them, 2 over 2 is just a 1. 2 over 4 is a half. 3 halves, 3 fourths, 4 over 1 is just 4. That's 2. That's 1. Becomes 3. 3 halves. 6 and 3. That kind of makes sense to everybody? Okay. So that was reducing them all. Now I go through and kick out redundant. Okay. Do I have 1 in there multiple times? That 1. There's 1. Got rid of it. Any 1 half multiple times? Any 1 fourths? Any 2s? Redundant 2, right? The 3 and redundant 3s. There. And there. And the redundant 6, right? And the redundant 3 halves. So that kind of cleans things up, right? Does that make sense? All right. So instead of actually having 36 possibilities, now we only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20. Okay, if we double, right? Okay. So that's convenient. That eliminates a little bit of our division. And the reason I do that, the reason I talk about that is because in the past, guys, I'd have somebody try 1, put that up in the box. And they go through and they say, okay, now I'm going to try 3 over 3 or 2 over 2. Put that in the box. And they're not thinking that they've already done that one. Okay, it's not going to yield anything different than what they've already done. So now we have a rule. Let me bring it up here. And I think I deleted it. This was easy. There it is. All right, so Descartes, René Descartes, French mathematician, you should have some familiarity with him. He's the guy that developed the Cartesian plane, the XY axis, okay? Very interested in polynomials, okay? So he discovered, okay, that when we're looking at our polynomial, when we look at the what we call variation of sign, okay, which is the plus or minus aspects of each term, right? When we look at those and they start to alternate or switch back and forth, if we count how many times they switch back and forth, it can lead us to an understanding of how many possible positive or negative zeros we might end up having. Okay. So what? And we're going to attack this by one rule at a time, or one aspect of the rule at a time. The first one says the number of positive real zeros of P of x either is equal to the number of variations in sign in P of x, or is less than that by an even whole number. Okay? Now, this phrase is kind of weird, but basically that's the concise way of saying start subtracting multiples of 2 until you get down to 1 or your first negative result. Okay? That's kind of wordy to say, so if I just less than that by an even whole number, it just says subtract 2, and then subtract 2 again, that would be reduced by 4, an even number, right? Or subtract 2 again, that would be reduced by 6, and you keep doing that until you kind of exhaust your ability to have positive zeros, or a positive amount of zeros. So what I always do is I write down like possible positive zeros, and I use this information to kind of help me guide my process when I'm going through. So if I look at this, okay, we just go sign change. So if I go from a positive 4 to a negative 16, that's counted as a one sign change. That make sense? Went from positive to negative. Now I go negative to positive. There's a second sign change. Is that okay? Is positive to positive, is that a sign change? Nope. What is positive to negative here? Is that a sign change? So I have 3 sign changes. Okay? So what this says is that I have, with 3 sign changes, you have 3 possible positive zeros, or that reduced by an even whole number. So what's the first even whole number that I would reduce that by? 2. You subtract 2 away from it, right? And you get 1. Now the idea is I keep subtracting 2 from that. But that's going to give me negative, right? And I can't have a negative number of objects. Okay? Because that's what a zero is. It's a physical object that we're going to have, right? I can't have a negative of those. Okay? So I have 3 or 1 positive zeros. Okay? That's nice to know. Because as I'm going through here, if I find out maybe the first try, that first consecutive division I do, and I get a 0 that was negative, okay, I automatically then know the other ones are going to be 3 positive ones. Does that make sense? Okay, and I can get rid of all my negatives. Now, another aspect of his rule of sign is step 2, which is a little bit more involved, okay, but it says that the possible negative zeros is equal to the sign change in P of negative x. Okay, so we're going to do a little work here. P of negative x. We have to rewrite our function. And the work here is not, there should not be like mentally taxing. It's just the amount of writing we have to do. We write that out, and now I go through and I evaluate that. So I'm basically looking at what is the positive or even negative values, okay? Because they're going to be multiplied together to give me a positive, right? Okay. So this is going to give me a 4x to the 4th. This thing here, it'll be negative x cubed, but times the negative 16 gives me a positive, right? Negative x squared is x squared, so it's going to be a positive 8x squared. Negative 16x, and then negative 12. So that's P of the opposite of x. So what that says, what that rule is getting at, it's the same thing now. Look at your variations and signs. Positive to positive, that's not a change. Positive to positive, that's not a change. Positive to negative, is that a change? Okay, so that's one sign change there. Is a negative to a negative a change? No. So what the second part of this rule says is that you have in p of negative x, the number of sign changes there tell you how many negative zeros you have, or that number reduced by an even whole number. So I had one sign change, right? So my possible negative zeros with one sign change is just 1. Now think about this. This is a 4th degree polynomial, right? This thing says, it's 4th degree polynomial, how many zeros are you going to have? You're going to have 4. Now they might have multiplicity, but you're going to have 4. If I have 3 positive zeros, how many negative ones am I going to have? 1. So does this tell you, based on this information, with this polynomial, that I got to have 3 positive zeros and 1 negative zero? Yes. Okay. Now, just the structure of your original polynomial, 5th degree, 6th degree, 7th degree, you're probably not going to be able to kind of delineate down and say, I absolutely know this is how many positive ones, this is how many zeros I have, or negative ones I have. But you can still write a statement like that, and it can still help you realize some things as you're moving through synthetic division. For instance, if I go through and I find 1 negative zero right off the bat, I'm going to go through and I'm going to erase all my negative P over Qs, because none of them are going to work anymore, right? I've got the one that I need, okay? So this information, before we even start doing anything, should allow me to kind of narrow in on our solution, okay? Now that's nice, that's awesome, okay? But there's still a lot of work to be done, all right? So what we've come up with, not we, because I had no part in this, but mathematicians came up with this rule. And this is actually a theorem. We can prove this. It's called the upper and lower bounds theorem. Okay? And it is kind of wordy, but basically, if we look at that first one, it says if we divide in synthetic division, and our object that's in the box, the value that we're trying to figure out in the box is a 0, right? If it's positive, you put a positive number in the box, it's synthetic division, okay? When you're done, if your quotient line, regardless of whether it gave you a 0 or not, okay? So this will be something that we gather from the quotient line if it has a 0 or if it does not have a 0, okay? You can address this in both situations. If the quotient line is constructed with all positive values or zeros. That's what it means by non-negative entries. Okay? So my quotient line is all positive numbers and zeros or zeros. Okay? That then tells me that the number in the box is what we call an upper bound for the real zeros of P. Meaning that that number in the box, let's say that number in the box is 3. And I go through my division, and my quotient is all non-negative values, okay? That tells me there are no zeros that are bigger than 3. And that would allow me to kick out some of my P over Qs, right? Okay, if it's for us, if 3 did that, we could kick out 4, 6, and 12. Eliminate some of our P over Q options, okay? The second part of this says, okay, what if we put a negative number in that box? Okay, put a negative number in that box, start dividing. Okay, this case says if your quotient line alternates non-positive and non-negative. I'll talk about what that means here in a moment. But if it alternates back and forth between pluses and minuses, then that negative value put in the box is the lowest bound for the values of P, or zeros of P. Okay, so it won't be any values. You know, if I try it in this case like negative 12. Negative 12 would give me maybe a positive, negative quotient line, okay? that would tell me that there's no zeros to the left of -12. That would make sense, hopefully, with our P over Q's, because those are the only options we have, right? There are no bigger negative values than 12 or -12. Now, this wording here is important. Non-positive and non-negative. Basically, what that's saying is that when you see a 0 in your quotient line, because we don't classify 0 as either positive or negative, right? A lot of times we say it's non-negative. But when we get that, and when we get a 0 in our quotient line, you can apply a plus sign or a negative sign to it to make it the way you need it. So the line would alternate. Does that make sense? So if I had a quotient line that looks like this, that said, let's go 2, -3, 0, -3, 2. Okay? Wouldn't it be really nice if I could consider my 0 being positive there? Because now they alternate, right? Okay? So I'm going to treat it like it was a 0. If it was, or a positive 0. If it was this way, negative, positive, looks like 3 positive and that negative, wouldn't it be nice if 0 was considered a negative number? Because now it would alternate, right? Okay? So you can address 0 how you need it to fit to your alternating sequence. Okay? I think it's a really good idea, guys, when you're doing these on your homework. Okay? Have these two theorems, Descartes' rules and these this boundary theorem, next to you so you can apply it. I don't want you to have to. Eventually you can. Okay, the way I remember, the way I associate them is if I'm putting a positive number in the box, I think positive numbers, I think bigger, I think upper, right? Does that make sense? Okay, so positive number in the box, upper bound, positive quotient line, upper bound. Okay, that's how I remember that first one. Okay, if I put a negative number in the box, negative number is going to be a lower bound. So it's my only option. Okay, and then with a lower bound, I'm looking for alternating sign. That's how I kind of link things together in my head. I don't remember that thing word for word, but try to make those associations. That make sense? Okay. So now, if we've got those beside us, or we're making those associations, we should be able to kind of get started with this thing. Okay. Now, just to, I don't know, prove a point, I don't know where to start with this. I don't know. You know, a lot of people want to start the first one here. That's fine. We'll start that one. That's fine. Start that one. That's fine. I'm just going to start somewhere. So we got 4, -16, 8, 16, -12. I kind of want to start, kind of what I did in last class, haphazardly somewhere in the middle of my list, just to kind of prove a point to everybody when we'll go through and do our synthetic division. If I put a 4 here, okay, because 4 is one of my options, right? Plus or minus 4. I'm going to bring my 4 down, bring my first thing down. Now I start multiplying. It gives me 16. So put that there. Gives me 0, 0. Gives me 8. Okay. Now 4 times 8 gives me 32. Add that down, gives me 48, right? 48 times 2 is 96. 96 times 2, what's that, 192? So when I add those down, I get a remainder of 180, right? A couple things or a couple things are existing here. Tell me some vital information, okay? Remember, this was a positive 4, right? When I put a positive number in there, my options are to figure out if that number is an upper bound only, okay? And I determine an upper bound by simply looking at the quotient line. If the quotient line is all positive or non-negative, so I do have a 0 in there, I can treat that 0 as a positive number. If that's happening, there are no zeros that are bigger than 4. Does that make sense to everybody? Okay? So there are no zeros bigger than 4 here. So obviously 4 is not a 0, and neither is 6, and neither is 12. Does that make sense? Okay? So I can kick those out. Now, the way I've written my P over Q's here maybe isn't the best way, because if I'm starting to erase things, I don't want to just erase the 6. If I erase that, there's a negative 6 that should be in there, right? Okay? So maybe when I did that plus or minus thing at the beginning, It's kind of foolish. And those are all kind of like notation, grammatical things that you got to pick up on and figure out that maybe they're useful, maybe they're not. In this case, I think probably not. Okay. But I now know 4 is not going to work. Positive 4 is not going to work. Okay. I know positive 6 is not going to work. And I know positive 12 is not going to work. Does that make sense to everybody? Now, it didn't give me a 0, but just because it doesn't give me a 0 doesn't mean it's not going to give me information. Okay. And that's the thing. Obviously, we prefer that it gave me a 0, but in this case, obviously it doesn't. Now let's try negative 4. Just because if I'm at 4, I tried positive 4, got rid of that, seen that didn't work, might as well start with negative 4, try that as well. The multiplication should not be all that difficult. Get 4 times negative 4 gives me negative 16, right? Gives me negative 32. That's going to give me, what, 32, 64, 128? Okay. So I add those down to get 136. All right, so 136 times negative 4 is negative 544. Okay. Add 16 to that. So now I'm looking at negative 5, what, 38? Now 28. All right. Okay, and really, I mean, I'm not even going to do this multiplication, but it's over 1,000, right? Add that down. It's not a 0, but it is a positive number, isn't it? Does that kind of make sense? Okay. Now I had a negative, right? Negative up here in my box. What's happening with your, you didn't get a 0, what's happening down here with your quotient line? Alternating. So what that tells me, negative 4 is a lower bound. So there's nothing that's going to work. Negative 4 did not work. Negative 6 isn't going to work. Negative 12 isn't going to work. Okay? Which is nice for us.
So, since it became alternating, does that mean that
right. So what we're saying here then is like our polynomial is going to do some stuff in between here and look for zeros, right? Right now, because we said positive 4 was an upper bound, so let's say 4 is right there, it means our zeros are going to happen to the left of positive 4, right? And now that we've got negative 4 as being a lower bound, it basically says our zeros now are going to definitely occur between negative 4 and positive 4. Okay? It just kind of systematically kind of shrinks that window down from negative 4 to 4 eventually as we go through this. So that's nice. Now, will every single time I do this, the first values I choose provide me something like that? No. Okay. You know, sometimes I'll get like a negative 4, negative 32, and then it starts alternating. Well, that's not collectively alternating. So then it doesn't yield me anything. It just tells me that that value was not a 0, right? But sometimes when I try values, if I get these results in the quotient line that match up these boundary theorems, then obviously I want to use that information. Hopefully that makes sense. And kind of think about this. If I told you at the beginning, we could have divided everything out by a 4, right? If I divide everything out by a 4, this thing becomes plus or minus 1 and plus or minus 3 in my values of p, right? Okay. Well, obviously, if those are my only values of p, then my zeros can't be things like 4 and negative 4. Okay. But obviously, if you neglect that GCF at the beginning, you would have to go through this process, and that would be what you learn as you go through the process. All right, so let's try it. I don't know another number 2 here. Let's try.
3 halves.
Say again?
3 halves.
3 halves. All right, so I'll bring my 4 down. Multiply that, so I get 12 over 2, which is 6, right? Multiply that using 10. Negative 10. Multiply that, so it gives me, what, negative 15? Gives me then 7, negative 7. All right, so now I get negative 21 halves. That one kind of stinks. Add those, so that's 32 halves. So negative 21 halves and 32 halves, so it's going to be what, 11 halves? And now if I multiply those, it's going to give me 33 fourths. And this would be negative 48 fourths. So now when I add those together, I get negative 15 fourths. The issue there is obviously multiplying by a fraction and getting, obviously because the fraction had denominator 2, when I had even numbers it was easy, odd numbers not so easy. But what's happening here? Positive, okay, and they're alternating, right? Or sorry, not alternating, correct? Okay, even if they were alternating, does the gain me anything? Not when this is a positive number, okay? When that's a positive number, the only option that we have to look at, because remember it says that if we divide by a positive number, that's if you have to be doing that, okay, before you can look at the then part of our conditional statement. So that has to be a positive number, and these have to be then non-negative, okay? Doesn't tell me anything. The only thing it tells me is 3 halves doesn't work, okay? Let's try, just because we're running out of time, you would probably maybe try negative 3 halves. You'll see that doesn't work either. Let's try, I think 1. Bring my 4 down. Go to 4. Negative 12. Negative 12 gives me negative 4. Negative 4, so it gives me negative 12. Did I do that right? Yeah, positive 12. So then multiply that by 1, and I get positive 12 there. So what's that tell me? Got a 0. Okay? Now, same thing happens, guys. If this was 1, okay, now I don't have a quotient line that is all positive values, but I could still apply the upper and lower bound theorem. I could still use that even when I get a 0. Does that make sense? And you can use that 0 at the end. You can either completely neglect it because it's at the end, or you can approach it and say, okay, it's either positive or negative how I need it. Does that make sense, everybody? Now, here's the thing. I don't know, and you don't know either, whether that 1 is going to be a double root. So what do we got to do? Do it again. Okay? And you got to do it again with that new line, that new quotient. Okay? So bring my 4 down. So it gives me then what, negative 8 there. Negative 8 gives me negative 12. Negative 12. Gives me a 0, right? Okay? Now what I want you to also understand is we did this in the last class, and we didn't get these values. We didn't try 1 first. Does that make sense? I think in the last class maybe we tried negative 3. So all our quotients were different, and the way we factored ended up being different. Does that make sense? Okay? But if we apply all our rules and procedures the same way, it shouldn't matter. We should still get down to the same answer. Okay? So, okay. Here's the nice thing. I've got 1 again. Okay, so we got double root so far. Do I know whether it's going to be a triple root? No, I got to try it again, right? Okay. I keep going with that root until I find out that it's not going to give me anything back that is useful. So I do this again. Bring my 4 down. Multiply. Give me 4. Give me negative 4. Multiply. Give me negative 4. Okay, so give me negative 16 as a remainder, right? Okay. So it's not a triple root. It's just a double root. Okay. Now I could have also made that distinction maybe another way. My cursor died. Hold on. Right. This was x to the 4th, right? So divided by x minus 1, essentially. X minus 1 is the factor. It gives me x to the 3rd. Divided that by another x minus 1. What's that give me here? X squared. Okay? Now, if it's x squared, what should we use to attack that? Yeah, I should go my quadratic processes. Either quadratic formula, you can use the AC method, you can use all those options we talked about at the beginning here. What should you do first of it? Bring 4 out. And that then, guys, is telling, I don't know what happened with my original P of X. Maybe let's scroll down. There it is. Remember I said at the beginning you could factor a 4? Wrong slide. There you go. You can factor a 4 out of this whole thing. We're seeing that 4 right here show up. Okay? So if that occurs, then you know that at the beginning you could have taken that out at the same time. Split 4 out, so it gives me then this, right? Okay. Does that factor? X minus 3, X plus 1. Okay. So now, look at my factor. We had P of X now is equal to, we have this factor of 4. We have X minus 3. We have X plus 1. And we have X minus 1 with a multiplicity of 2, right? Now think about this. Does that match up what we said about the rule of sign, okay, that said I'm going to have 3 or 1 positive zeros. How many positive zeros do you have here? That's 1. That's 2. But 3, right? Okay, because it happens twice. So we got 3 zeros. Is the X plus 1 a negative 0? Yeah, so that can help us kind of confirm that we have done things correctly. We can also use those features, those facts, as we're working through. Maybe when I do my synthetic division, guys, maybe at this stage I'll just show you what could happen. Let's say for some reason, maybe I chose instead of 1, I chose negative 1 right here. Gives me 4. That's terrible. Put my 4 down. All right, so gives me then what? Negative 4 here. So I get negative 20. Gives me 20 there, so 28. Negative 28. So it gives me negative 12. Positive 12, right? This would have been a negative 0, right? I'm only supposed to have 1 negative 0. So can I then go through my P over Qs and remove all the negatives and say I don't have to try any other negative divisors? All right, so that's the benefit of having that information in front of us as we're going through these problems. Why are we doing this, though, guys? Why are we interested in this process? What is our overall goal? Okay, yeah, we're interested in graphing these things, right? And right now, that tells us a lot of information. It's a 4th degree polynomial. It's going to have 4 zeros. We got 1 at positive 3. So 1, 2, 3. So there's a 0 there. It is a multiplicity of 1, so it's going to pass through, right? Okay. Let's go to this positive 1. So that's going to give me a 0 at negative 1, right? Multiplicity is odd, so it passes through. Now this one's a multiplicity of 2 at that point right there, right? Let's just put multiplicity 2. Okay? It's 4th degree, and A is positive. Does that tell me my end behavior looks something like this? My y-intercept, negative 12, correct? Okay? And in the factoring process, guys, tells us, well, if we pass through here, this was an odd multiplicity, we're going to pass through there. Now, I'm not sure, again, because the idea of maximum and minimum, I'm not sure how this relates to negative 12, and that's a terrible job drawing. But now I'm going to come back up, and what's going to happen at 2? Yeah, it's not that 1, it's got multiplicity 2. We're going to touch it, right? And we're going to be tangent, we're going to bounce back down. And then what's going to happen for me to get through here? I'm going to have to turn, right? And now I've got a better sketch of 4x to the 4th minus 16x cubed plus ax squared plus 16x minus 12. Okay? Because at the beginning of P of X, that's my expanded P of X, the only option I have for graphing that when it's expanded is to set up a T-chart and choose X's and Y's, right? And we know that's kind of like just closing your eyes and throwing dark to the dartboard. You don't know which ones you're going to get. You don't know which ones are going to be useful. Does that make sense? This is a process that is much more informative, okay? And obviously then when we learn a little bit of calculus, it's going to give us a much more comprehensive and accurate graph because of those minimums and maximums that we could find, okay? But that's the reason we're doing some of this stuff. We're also interested, a lot of times, guys, in learning, you know, when is this thing equal to 0? Because when things are equal to 0, that's a very useful relationship to explain real-life situations. And this is how you do that. Okay? We have to change that polynomial down to a series of products of factors, and we can move on from that. Okay? Okay? What the fundamental theorem of algebra basically says to us is that every polynomial we come across, that can be done to. Okay? So we're going to kind of address that next couple days. The one thing I want you guys to understand is that when we factor these, we might not always get real solutions. So when I had that, was it 4x squared minus 4x plus 12 or something like that, that last quotient, that thing might factor to give you complex roots. Does that make sense? And the problem with that is if we don't address our quadratic approaches with that right away, and I continue with synthetic division, I might exhaust all my Q or Q's and find out I just wasted a bunch of time because none of them worked, right? If I would have jumped straight to the quadratic formula, I would have gotten those non-real solutions very quickly, all right? So linear quotient line, that's the one thing that I see people all the time through 12 years of teaching this, they waste all their time on doing. When they get to x squared in their quotient line, they keep going with synthetic division. Use your other approaches, okay? It's going to save you a lot of time. Tomorrow, guys, what I want to do is kind of work through a couple more examples of this, but at the same time, maybe give you, I still want to use these theorems, but give you kind of an idea of how we can maybe approach it a little bit quicker, okay? We'll do that tomorrow.
Have a good day, guys.
Thanks, you too.